Section 1.5, goals. We're going to deal with one-sided limits, and we're going to find out what happens around vertical asymptotes. We're going to start off, first thing I'd like everybody to notice is this little 4 with the minus sign next to it. So what this means is we're looking at the limit as x approaches 4 from the left-hand side. So if there's a minus like that, so if we say limit, if we see limit as x approaches 4 with a minus, we're talking about from the left-hand side. And if we wanted it from the right-hand side, we'd be talking about the limit as x approaches 4 with a little plus sign right there. So the difference is the sign minus, meaning coming from the left-hand side of it, plus coming from the right-hand side. And to contrast that, let's look at this problem number 2 down here. If we see it with no sign, we're talking about from both sides. So something to keep in mind. Limit as x approaches 4. All right, so normally with limits, what we would do is we'd start off, we'd try direct substitution. If we try direct substitution, we're going to end up with a 0 in the denominator. Well, we know limits can't be undefined. We can't factor and cancel. We can't do any of those good things. So what we actually have figured out then, since I can't do this, is that what we really have is we have a vertical asymptote at x equals 4. So if I came over to the graph, I don't really remember what this graph looks like from my days in pre-calculus, but I know I have a vertical asymptote there. So what we're going to do, if our last resort, if we can't do direct substitution, we can't use the other techniques like factor and cancel, rationalize, etc., what we're going to do is we're going to try to estimate this limit. Last resort. And the way we're going to do that is we're going to take the limit as x approaches 4 from the left-hand side of 1 over x minus 4. We're going to see, well, pardon me, let's pick a number that would approximate approaching 4 from the left. Well, pardon me, I could use 2. That's a number that's smaller than 4. I could use 3. I could use 3.5. All these numbers would be to the left of 4. What we'd like is we'd like to come up with a number that would give us an idea what happens if we were to plug it in, and we'd like it to be pretty close. So let's take a number, 3.9. I'm going to take 3.99. That should give us an idea of what's going on to the left of 4. If I take 3.99 and plug it in, what I would end up with here would be 1 over 3.99 minus 4. Well, that would give us a number like 1 over negative 0.01. 1 over negative 0.01. That's negative 100. That's a big number with a negative sign on it. So that must mean that this graph is going down, 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 down. So what would happen if I picked a number like 3.999? If I add another number to the end of this, I add another decimal place here, and I add another 0 here. So the closer the number is to 4, the larger the result with a negative sign on it. Well, what does that mean? That means from the left, this thing is really heading downward like this. And what would this limit be? This limit would be negative infinity. Negative infinity. So our last resort, if we can't do any of the other techniques that work for limits, is we estimate it. And if it's around an asymptote, we're looking at either a positive or a negative infinity. All right, let's look at number 2. Now, again, as I look at this problem, direct substitution is going to fail miserably. I'm not going to be able to make it go. So what I have here is I've got a vertical asymptote at x equals 1. I know that. I can't take it out of the problem. So if I went to x equals 1, I'd have a vertical asymptote. Well, what does this graph look like? Well, 1 over x minus 1, if I remember correctly, that was a graph that would look something like this. 1 over x graph had this kind of behavior going on, and I remember that from my days in pre-calculus. So now let's algebraically support what I just drew, because maybe you don't remember that. My guess is you probably don't. So let's estimate. Let's start with doing the limit as x approaches 1 from the left of 1 over x minus 1. Again, factor and cancel, no good. So let's estimate it. Let's use a number like 0.99. If I take 0.99 and plug it in directly, directly substitute, what I'm going to look at is how about 1 over negative 0.01, which is going to give us a result of about negative 100, which means this limit, as we approach this thing from the left, is really negative infinity, which makes sense because according to this graph, we've got this thing heading downward to the left of 1. Well, let's contrast that with the limit as x approaches 1 from the right-hand side. Again, same technique, same deal, but this time let's use a number like 1.01. Well, if I do that, I'm going to have 1 over positive 0.01, which is going to give us positive 100 as a result, which makes sense because according to this, we're saying this graph is going to continue to go up. So what is this limit? This limit would be positive infinity. Well, if one of them is headed toward positive infinity and the other one's headed toward negative infinity, the limit as x approaches 1 from both sides of 1 over x minus 1 would not exist. Why doesn't it exist? Because those two values don't match. And again, looking at the graph, one side's going up, one side's going down, headed toward the same x value. They don't agree. Limit doesn't exist. And we just showed it two ways. We showed it graphically, and we showed it algebraically. All right, last one, vertical asymptotes. Vertical asymptotes, a lot of people are going to look at this problem and they're going to say, okay, vertical asymptotes, I'm going to set the bottom equal to 0. Or I'm going to factor the bottom to x minus 2 and x plus 2, which means I'd have two vertical asymptotes. That's not necessarily true. What we do know is this thing is discontinuous at both x equals 2 and x equals negative 2, but we have to do more work to figure out what types of discontinuities those are. So if we look at the numerator of this thing, we could factor this numerator into x plus 4 and x minus 2. Well, notice that common quantity on both the top and the bottom of an x minus 2. Well, what effectively we just did is we just were able to remove the x minus 2 quantity from the problem. Well, if I set x minus 2 equal to 0, I just effectively removed the x equals 2 from this problem. And if I do that, what I really have is a new problem that says this f of x is really the same thing as x plus 4 over x plus 2. Well, what does that mean? We just removed the x equals 2 from the problem. What that means is a removable discontinuity and if that's a removable discontinuity, what that really means is there's a hole in the graph at the point, a hole at x equals 2. Well, if we wanted to find the y-coordinate, remember I'd finish off the limit by directly substituting into this x plus 4 over x plus 2. 2 plus 4 would be 6. 2 plus 2 would be 4. What I really have is a hole in the graph at the point 2. What did I say, 6 over 4? 3 halves. And then if I wanted to know, well, what about this x plus 2? This x plus 2 in the denominator, well, that means that this x equals negative 2 thing is still a problem. That means I just found a vertical asymptote at x equals negative 2. So the question says, find any vertical asymptotes? There is a vertical asymptote at x equals negative 2 because we weren't able to remove it from the problem. And if we wanted to make a graph of this whole thing, we'd put a vertical asymptote at x equals negative 2. We'd put a hole in the graph at the point 2, 3 halves. And what we're going to have, and I don't remember how this graph should look off the top of my head, I think it looks something like this. What you could do right now is put this equation in and see what happens at x equals 2. If you try the value at x equals 2, you'd end up with a hole in the graph at the point 2, 3 halves. Or in other words, you do value at x equals 2, it wouldn't exist because of the hole in the graph.